We used implicit differentiation to show that if you have x squared plus y squared equals 1, you can take the derivative and get 2x dx plus 2y dy equals 0. Now, can we do something like divide this all by dt? Maybe. Okay, if we did that, we'd have 2x dx dt plus 2y dy dt equals 0. It's a meaningful statement. So if you go straight from the original equation, x squared plus y squared equals 1, down to this third line, what you do here is you can take a derivative. The derivative of x squared is dx. But dx, the question is, how is x changing? Okay, x squared changes with a derivative of 2x with respect to what? It can be with respect to time. And when you put it over dt, it is with respect to time. And these are actually called related rate problems. Okay, and the way they work is you're given some kind of an equation and you take the derivative, but everything is with the dt. You know, you could have all types of problems. And so if you had, like, for instance, let's say you had the area equals pi r squared, and we're looking at a related rate problem. So what you do is you take derivatives with respect to t. So you would have like dA dt, okay, equals, just keep taking derivatives, 2 pi for each variable, 2 pi r dr dt. And generally speaking, in these types of problems, you're going to be asked to find one of these. Say, how is the area changing with respect to time? And you would usually be given the other one. When the radius is changing, at a rate of like 3 units. And so dr dt would be 3. And at this point, r is 6. Okay, so you just plug in for everything else. So related rates are generally presented as word problems. And so you're given different examples to work through. We can extend this one to an example if we imagine, say, there's an oil spill, okay? And let's just say that the radius of the oil spill, the rate of change, okay, it's changing at like 2 feet per second, okay? So we would plug in here, dr dt is 2. And we want to know how fast the area of the oil spill is changing when it's at 10 feet, okay? So then we would plug in for these numbers, 2 pi and 10, and we would get that dA dt is changing at 40 pi feet per second. Okay, so that's an example of how related rates can work. Okay, once again, in this example, we're saying, hey, there's an oil spill, and then we're provided with additional information. The rate of change, the increase of the oil spill as it's going outward, the radius is 2 feet per second. The radius, it's okay. In math, sometimes we leave off the units. We add a lot at the end, but you gotta be careful if you do that. So this would be 2 feet per second, but the radius is at 10 feet. So how fast is the area of the whole oil spill changing at 10 feet? That would be feet squared per second. Okay, let's do some other examples. Okay, consider the following. Let's have, say we have a cube, okay? And the cube is increasing. We'll do something sort of similar. Increasing at, let's keep our numbers nice and simple. Let's just say 1 feet per second, okay? So 1 feet per second. Okay, and then what we're gonna say is when the cube, I'll just say s. So when the side of the cube, when s is equal to, give a number, say 3 feet, we want to know how fast the surface area is increasing, okay? So what is rate of, increase of surface area? We'll call that SA. Okay, so this is a related rate problem. You give us some information. We've got to turn it into equations. Okay, so the cube increasing is a volume increase. Okay, so how do we do that? Well, we know the equation for the volume of a cube, right? It should be relatively straightforward. Volume equals the side cubed. Now, what we want to know is the rate of the increase of the surface area. So the surface area of the cube, we can just use A here, is going to be each of the sides squared, added up. There's 6 of them, so it's 6s squared. So we have these two equations that we are working with. And there's some different ways to go about this one, but note that they're giving us sort of like dv dt, okay? We're given, in effect, we can put the givens up here. Givens are that s equals 3, and significantly, the cube increasing at 1 feet means that dv dt equals 1 foot per second. Okay, so we're given dv dt, but we want to find dA dt. So if we just look at the second equation and we take the derivative, the way you do that, dA dt equals, take the derivative, 12s ds dt. Okay, that's great. And the issue is we don't have ds dt. We only have dv dt, okay? You need to use the other equation to actually figure this out. And so the other equation, right, starting with v, is dv dt equals, we'll take the derivative, 3s squared ds dt. So we can solve this second one for ds dt because we have everything else. We've got dv dt is 1, we've got s is 3, s is 3 squared, and ds dt is what we're trying to figure out. And so we can do that. That's 3 cubed, 1 over 27 is ds dt. Now, if that's what we wanted, we would be done, but it's not. We want dA dt. So now we can come back up here and plug it in. And so we've got this 12 times 3 times 1/27th. And that is going to equal, that's 36 over 27. So if we divide by 9, it is 4/3. So we get 4/3. And again, it's an area changing with respect to time. So once again, it'll be feet squared per second. Okay? So that would be the solution here. Okay, let's do another one. Related rates, by the way, I should mention, they really vary in terms of how challenging they might be depending on, like in this particular case, we needed 2 equations, sometimes you only need 1, and sometimes the geometry might be harder than other times, when doing homework, look up formulas, okay? And it's sort of a key with these that you need an equation, maybe 2, and then you have to find a way to have them work together. Okay, so consider the following one. Okay, so let's say you have a point, of intersection, and you have two vehicles that leave this point of intersection in different directions. Okay, so vehicle A, let's say, is going 60 miles per hour, and vehicle directly east. And vehicle B is going directly south, say 40 miles per hour. And the question is, so something like, after, could be any number, let's say after 2 hours, what is the rate, what's the change of the distance between them? How is it increasing? So what we want to know is rate of increase of distance. Let's call that a capital D here. And it needs to be some kind of context. So when what? Well, it's, after 2 hours. Okay, so this is a related rate problem, and we need to use the distance formula. So the distance formula is as follows. D equals square root of, and then it's x2 minus x1 squared, plus y2 minus y1 squared. Okay, this is from Pythagoras. Why did I say it's from Pythagoras? It's not a squared plus b squared equals c squared. Well, it actually is in coordinate geometry if you draw a right triangle. Okay, so in this particular problem, this is happening after 2 hours. Now, so the idea is, you've got maybe A is here, B is here, and we want to know the distance between them at this given moment in time. Now, if you look at this problem, only A is going in the x direction, and only, I didn't write it, I guess, only B is going in the y direction. So there is, if this is 1, x1 is 0, right? I'm sorry. Did I say that right? No, x1 would be 120, but x2 would be 0, and y1 would be 0 because there's no y in motion. So basically this problem, because one of these is 0, this problem reduces to a much nicer x squared plus y squared. Certainly you could get the subscripts right and say, oh, it's x1 squared plus y2 squared, but if you only have one x and one y, it's a little bit easier to eliminate the subscript. Okay, so we're making good progress. We need to take the derivative, okay? So let's do that now, and we get this dd, sort of interesting, dt, equals what? Okay, this is a square root. We've had a lot of these, so it's 1/2, so it's going to be 1 over what? That, the x squared plus y squared, and the square root. But then times the derivative of what is inside, okay? And the derivative of what's inside now is going to be 2x. We just took an x derivative. This is a related rate problem. You must write dx dt plus 2y dy dt. Okay, and now we should be able to plug everything in. Okay, because if they've gone 2 hours, we know where they are. Okay, because we're given their rates. So let's try to plug in here, and we get what? We get, okay, what's x? X is going to be point, like the car A, at the 120 mile marker, so it's 120, because it's got 2 hours later, right? Oop. And then I've got to put in my dx dt. So it's going at 60 miles per hour, right? Times 60. because that's the change in the x direction. And then my y would be at the 80-mile marker, because 40 miles per hour, 40 times 2 is 80, times dy dt, and that's going to be the 40. And that is all over the square root of the squares here, and that's these numbers, these x's are already in parentheses, 120 squared plus 40 squared. And, you know, like, yeah, I guess I would simplify the numerator here without a calculator. I'm not going to bother with the denominator. So what do I have in the numerator? It's kind of, okay, so 2 times 6 is 12. 12 times 12 is 144 with 2 zeros, so 144, 0, 0, plus, what's the second one? Once again, 2 times 4 is 8. 8 times 8 is 64 with 2 zeros. And so just a little simplification here. And I'll leave it like this. Although it's good to take these a little further. Okay, so this is going to end up giving you the rate of change of the distance over time. So what we have here is kind of a new idea, which is really cool, that you can take derivatives sort of with respect to something different like time, right? When you have this equation, there's no t involved. It's not there. None of our starting equations had t in them. But we can take derivatives with respect to time to see how things would change over time. So this allows you to solve some really cool problems. Like, you could measure in an oil spill, how quickly the spill itself is moving out, which is the rate of change of the radius over time. But with a little calculus, you can use that then to figure out how the entire spill, the entire circle, is changing with respect to time. In this problem, we had to use 2 different equations with respect to time to figure it out. Then we had a distance one. Maybe the formula is a little more complicated. You have to look carefully to be able to plug things in. Okay, all the related rate problems are different. You need an equation, you need to take the derivative, you need to do it with respect to time, and if that doesn't give you enough, you need to find potentially a second equation and to look carefully at the original problem. Related rate problems can be challenging, but they are one of the critical applications of derivative problems in calculus.